so we can finish at a good time here. Same as usual, just go through the set of practice problems that are posted up in D2L. And if there's one you want to see, I'll just ask if you want to see this one. And if you want to see it, say yes. If you don't want it, don't say anything. And if somebody else wants to see it, we'll do it. If nobody says anything, we'll just move on to the next one to make sure that we get the problems covered that everybody really wants to see. So number one. Yes? Okay. So number one says, what is the pH of a solution that has a concentration of H plus equaling 3.5 times 10 to the minus 6? Okay, so we didn't do a whole lot with concentration of H plus, but remember I mentioned very close to the beginning of the unit that the concentration of H plus is really just the concentration of H3O plus. We don't really have lone protons floating around in solution, but that used to be a way of expressing that concentration. So here we have a concentration of H plus is equal to 3.5 times 10 to the minus 6, and we know that pH is equal to the negative log of the concentration of either the H plus or H3O plus. So the pH here is going to be equal to negative log of 3.5 times 10 to the minus 6. And when you do that, you get 5.46 or 5.5 to just one sig figure. Questions at all on that? All right. Number 2. Yes? Okay, so number 2 goes back the other direction. Okay, so here we're looking for the H plus concentration in a solution where we know the pH. And so same thing as before, so we can say the concentration of H plus is going to be the same as the concentration of H3O plus. Okay, so we know the concentration of H3O plus is equal to 10 to the minus pH. Okay, so that's going to be equal to 10 to the minus 10.9. And when you put that in your calculator, I got 1.26 times 10 to the minus 11. And to 2 sig figs, we get 1.3 times 10 to the minus 11. Okay, so 1.3 times 10 to the minus 11. Make sure that you do know how to go back and forth between concentration and pH. Let's see, number 3. Yes. So here we're looking for, now number 3, if you, hopefully you saw the note that was posted on D2L with the exam, it says that there's an error and B is the correct answer. Yeah, it says that right underneath where you download it. I have changed that since, but I only changed that this morning. So if you downloaded those before this morning, it said E before, and that's not the correct answer. The correct answer is B. Do you still need to see it? Okay, I had a feeling that may have been the problem. All right, number 4. Good. Number 5. Yes, I saw that one coming. So for number 5, we've got to remember what amphiprotic means. So remember, amphi kind of means both, like amphibian means both land and water. Amphiprotic means it can either gain or lose a proton. So it can act as either an acid or a base. So what we really need to look for in the species here are things that can act as either an acid or a base. So if we look at Cl minus, can that both gain and lose an H plus? It can. It can't lose an H plus, doesn't have one to lose. Okay, so that's not the correct answer. How about HClO4? Okay, that one we need to think about a little bit. HClO4. So what is HClO4? Perchloric acid, and it's more importantly one of our strong acids. It's one of the says 6 strong acids. Okay, those 6 strong acids, they lose H pluses readily, completely. They do not gain them. So they act only as acids. So it can act as an acid, but it cannot act as a base because it's a strong acid. So that one doesn't work. NH4 plus. Okay, NH4 plus. One of the ways that, remember we said for a bronzosyluric acid, in order to act as a bronzosyluric acid, as a bronzosyluric base, it has to be able to accept that H plus. Well, with NH4, it has no way to do that. If you looked at the dot structure for NH4 plus, it looks something like this. And there's no way to form a bond with another proton. The H plus has no electrons. The NH4 has no additional electrons with which to form a bond, and so it can act as an acid. It can lose an H plus, but it has no way to pick one up. Okay, so that one doesn't work either. So the correct answer here is D, which is HCO3 minus. So that's the bicarbonate ion. Okay, if it gains an H plus, it becomes H2CO3, which we've seen before. That's carbonic acid. And if it loses an H plus, it becomes CO3 minus, which is the carbonate ion. So that's viable as well. So that's why the answer is that bicarbonate ion, HCO3 minus, because it can either gain a proton or lose a proton and become a common substance there. Our last one there, just the last option, is OH minus. Is the hydroxide, so that's basically our definition of a strong base, hydroxide. Is that going to lose an H plus as an acid? Not very likely, because it's a strong base. Okay? Very good. And it certainly isn't going to do it in aqueous solutions. It is possible to pull an H off of a hydroxide, but it's really hard to do, and you're not going to do it in water. It's got to be in some weird exotic medium there. It's definitely not something we talk about in class. Questions on that one at all? I know a lot of people struggle with that. Okay. Number 6. Yes. Okay, so for number 6, the way to do these, so we're looking for the conjugate acid of H2PO4 minus. Okay, well, if we're looking for the conjugate acid, then H2PO4 minus must be acting as a what? As a base, because what has conjugate acids? Bases have conjugate acids. So that means that this would be a base, and if it's a base, that means it's going to add a proton. It's going to pick a proton up, and when that picks a proton up, what does it become? It becomes H3PO4. So H3PO4 is the conjugate acid of H2PO4 minus. We could have flipped that around, and we could have said, what's the conjugate base of H3PO4? And then H3PO4 would be acting as an acid, and H2PO4 minus would be its conjugate base. Any questions at all on that one? All right, we're moving right along. We should be done early tonight. We'll see. We're not to the hard stuff yet. Let's see. Number 7. Is that it? Yeah? Okay. So number 7 just says, which of the following is true for a sample of pure water at 25 degrees Celsius? Okay. Well, let's see here. The answer there is E. All of those are true. And let's take a look at each one of those. So A says, there should have concentration brackets around those. I don't know why they don't. So concentration of H3O plus is 1.0 times 10 to the minus 7. Okay, that's certainly true. Concentration of OH minus is also equal to 1.0 times 10 to the minus 7. Remember, so just pure water, it dissociates into, or it autoionizes by colliding, and you get an H3O plus ion and an OH minus ion. and those concentrations are equal in pure water. Okay, and they both equal 1 times 10 to the minus 7. Okay, if we multiply those together, we get the value of Kw, and that is 1 times 10 to the minus 14. Now remember, that's the value of water at 25 degrees Celsius, just like any equilibrium constant. If we change the temperature, we do change the value of that equilibrium constant. Most of our stuff is done at 25, so it's not that big a deal. And then if Kw is 1 times 10 to the minus 14, then the pKw, which would just be negative log of the Kw, and that's going to give you a value of 14. So that's true as well. And so all of those above are true. Which one of those three a little bit for anybody who wanted to see it? Any of those confusing on there? Okay. Let's see. How about number 8? Yes. I think I got enough room on this here. So number 8 says, what is the pH of a 0.010 molar sodium hydroxide solution? So the first thing you've got to make sure you recognize on this one is that sodium hydroxide is a strong base. It's one of our strong bases because it has a group 1A metal and the hydroxide on it. And those are always going to be a strong base. And the strong bases are going to dissociate completely. So NaOH is going to turn into sodium ions plus hydroxide ions. Okay, 100% reaction, completely dissociated. Okay, strong electrolytes. So if the concentration of the solution is 0.01, that really means that the concentration of my hydroxide is 0.010 molar. Okay, so now I know my hydroxide. I can find the POH. Okay, and so the POH is just the negative log of my hydroxide, so the negative log of 0.010. Okay, and that gives me a value of 2. And then the pH is going to equal 14 minus the POH, which is going to be 14 minus 12. I'm sorry, 14 minus 2. And you get an answer of 12. Okay, so the pH there is 12. Okay, which we would expect. It's just a sodium hydroxide solution, so it should have a fairly high pH. Questions at all on that? All right, let me turn my page here. Oh, that was 8. Number 9. Yes. Okay, so number 9 is just going to be an ice box. So now we've got an acid in solution, just an acid in water. And we're going to allow it to dissociate. We're not reacting with anything. We've got a 2 molar solution. And we're given a Ka. So we had a problem very similar to this in class some time ago. And so even though we don't know the formula for benzoic acid, it's not that important to know. All we need to know is that it's an acid, and it's going to lose an H plus to water. Okay, and we're given a Ka there. So we're just going to write our formula for benzoic acid. We're just going to call that H-benz. Okay, the H in front of the benz, the H is the one that's going to be lost to the water. So anytime we have an acid or a base in water, we're going to react it with water. Okay, so the acid is acting as an acid, which means that the water is going to act as a base. So the H-benz is going to lose an H+, and the water is going to pick it up. And because we have a Ka, that is going to be in equilibrium. So that's going to give us H3O+, and some benz minus. Okay, so now we can icebox that. Okay, and we have a 2 molar solution of H-benz. We have no H3O+ and no benzoate to start with, benz minus. We're going to lose some amount of the H-benz. We're going to gain some amount of the hydronium, and we're going to gain some amount of the benzoate. And so we end up with 2.0 minus X, and X for our concentrations there. And we just set up our Ka. So the Ka here is going to be equal to our products over reactants. So the concentration of H3O plus times the concentration of the benzoate all over concentration of H-benz. Okay, so that's going to be equal to 6.50 times 10 to the minus 5 equaling X times X all over 2.00 minus X. Okay, we have a pretty small Ka there, 6.5 times 10 to the minus 5. So what we're going to bank on here is that this X that we're subtracting from the 2 is much smaller than that value of 2. So we're going to say that 2 minus X is still basically equal to 2. So that allows us to get rid of that X there. If you have a solver function on your calculator and you know how to use it well, you don't have to throw out the X. It may give you just a slightly different answer, but it's still going to be really close because this is an approximation that we do. But it'll still be really close. So we have 6.50 times 10 to the minus 5 is equal to X squared over 2. And when we solve that for X, we get a value of 0.0114. And that, of course, is equal to concentration of H3O plus. And so I can now take my pH. It's not looking for the pH. It's just looking for that value there. So that's 1.14 times 10 to the minus 2. Okay, so the answer there should be E. Okay, questions at all on that? We've been doing so many more problems that are more difficult than that. It's easy to forget some of the ones we started doing. Don't make them more difficult than you have to. Let's see. How about number 10? Yeah? Okay. So 10, we have a Ka for H2CO3. Okay, and we're looking for the Kb of HCO3 minus. Well, if we look at those two substances, what do we notice about those two compounds? Yeah, they're conjugates of each other, and we know that because they differ by just a single H+. So if you have two compounds that differ by a single H+, they are conjugates of each other. And if they're conjugates of each other, that means that their Ka times the other's Kb is going to be equal to Kw. Okay, so we're given the Ka of the H2CO3, the carbonic acid, and we're looking for the Kb of HCO3 minus. So we can rearrange this equation and we can see that the Kb is going to be equal to the Kw over the Ka. Okay, and Kw is 1.0 times 10 to the minus 14. Okay, so that's the equilibrium constant for water at 25 degrees Celsius. That's what it always is. It's 1.0 times 10 to the minus 14. If you need a different value of that, because maybe the problem's at a different temperature, they'll tell you this is what the Kw is at that temperature. But if you're not told anything else, just assume it's at 25 degrees Celsius, and that's what your Kw is going to be. Okay, so now we take our Ka that we are given at 4.2 times 10 to the minus 7, and we solve that for Kb, and we get 2.38 times 10 to the minus 8, and to 2 sig figs you get 2.4 times 10 to the minus 8, so the answer there should be C. Yes?
So if it were conjugate pairs, would you not do that?
Yeah, if they were conjugate pairs, you can't do anything. Yeah. Because only conjugate pairs have that relationship. All right. That was number 10. Number 11. Yeah, 11's a little nastier than I would normally get on a test. It's not hard, but it did throw a little bit of a twist in there that you're probably not used to seeing. Okay, so the first thing that we've got to make sure that we recognize on number 11 is that we have a salt. We have a sodium salt, so NaCN. And anytime that you have a salt, just break it apart. Okay, because all your sodium stuff, or your potassium stuff, lithium stuff, it's going to disassociate completely in water into the cation and the anion. Okay, so NaCN is really broken up into sodium ions and cyanide ions when it's in solution. Now the sodium ions we should recognize as the counter ion to the strong base sodium hydroxide, and those counter ions have no acid-base properties. The cyanide, however, is the conjugate base of HCN, which is a weak acid, and we know it's a weak acid because it gave us a Ka or a pKa of it, and if it has a pKa or a Ka, that means it's weak. It's a weak acid. And Cn minus is the conjugate of it, which means that it is a weak base. Okay, so if we have a weak base in an aqueous solution, that weak base is going to hydrolyze, which means it's going to react with water. Okay, so that Cn minus is going to react with water, and because it's a base, it's going to take an H+, so it's going to form HCN and OH-. Now, since this reaction gives us a source of OH-, what do we expect the pH to be? Greater than 7 or less than 7? It should be greater than 7. We should get a basic solution here. Okay, so let's go ahead and icebox this. Okay, our Cn minus concentration is 0.5. Now we don't care about the water. The HCN is 0 and the OH- is 0. Okay, we're going to lose some of that Cn minus. We're going to gain some HCN. We're going to gain some OH-. So we have 0. Left off the 500 minus X, X, and X. Now, the one place people make a lot of mistakes here is they're given a pKa of HCN, easy enough to change that into a Ka, but is this a Ka reaction? No, this is a Kb reaction because it involves something taking an H+ away from water. Okay, so this is a Kb reaction, so we've got to figure out the Kb for the Cn minus ion. Okay, now, and like I said, in this problem, they give you a pKa of HCN. And I wouldn't normally do that because that's not what you normally look up. Normally, when you look up something for an acid, you find the Ka. So it's a little bit of a twist on a problem, but it's still not too bad. So what we can do over here, so we see the HCN has a pKa of 9.31. It's going to do pKa is equal to 9.31. And what that means is that the pKb, I'm very good with my letters here, of Cn minus is just going to be equal to 14 minus 9.31. And so the pKb of the cyanide is going to be equal to 4.69. Okay, so now I know the pKb. I can find the Kb just by doing 10 to the minus pKb. So the Kb would be equal to 10 to the minus pKb, and so that's going to be equal to 10 to the minus 4.69, and so the Kb for Cn minus is 2.04 times 10 to the minus 5. Everybody okay with that? Any questions on what I did there? Like I said, I wouldn't normally do that. This just comes out of the test bank, and I write the test questions. I don't write these. Okay, so I would just give you the Ka. All right, so now we know the Kb of the cyanide ion, and we can set up our reactions. So the Kb is going to be equal to the concentration of products over reactants for our equilibrium. Concentration of HCN times concentration of OH minus over concentration of Cn minus. That's going to be equal to 2.04 times 10 to the minus 5. So that's equal to X times X all over 0.5 minus X. And again, we've got that X on the bottom there we've got a fairly small KB, so I'm pretty sure that that x is going to be small enough that we don't have to worry about it when we subtract it from 0.2. And so that gives us 2.04 times 10 to the minus 5 is equal to x squared over 0.500. And when we solve that out, we get an x value that's equal to 3.20 times 10 to the minus 5. Okay, so that is much smaller than 0.5, so we don't really need to worry about that. Now, the other important thing is to recognize what is that x value equal to? Well, it's equal to the concentration of HCN. We don't care. It is equal to the concentration of OH, which if we're looking for the pH, that's a big deal. Okay, so that's equal to the concentration of OH. So now I can take the negative log of that x value and get a POH. Okay, so I know the POH is equal to 2.5. I hope you guys heard that, because that was a weird noise. Was that a phone? Oh, okay. I didn't know what it was. It sounded like some alarm somewhere. So pH is equal to 11.5. Yeah? Oh, I was wondering about that. That 10 to the minus 5 looks really weird. Okay. Oh, I think I did. I think I just can't read my writing. It is a 10 to the minus 3. That makes more sense for the POH, actually. It's just a typo. The calculation's fine. So you get a POH of 2.5 and a pH of 11.5. And again, we would expect a pH that's basic because we have a source of hydroxide. Okay, questions at all on that one? Any questions on that one? You guys know the story of what happens when a bell goes off, right? Yeah, when the bell goes off, an angel gets its wings. When you're my age, you just hope it's not you. Freak! All right. I woke you guys up. All right, let's see, number 12. Yeah, okay. Got to ask that one a few times today as well. So for number 12, it says, which of the following solutions is acidic? So let's just go through each one of these. So the first one is F minus. So what is F minus? What's the fluoride ion? It's that's your cue, by the way. Conjugate base of a weak acid, and that means it's basic. Okay, so this is a conjugate base of a weak acid, and that means it's going to be basic. Well, that basic is not acidic, so it's not F minus. Magnesium hydroxide, MgOH2. Okay, magnesium, group 2 metal. Hydroxide, well, it's a group 2 metal hydroxide. And what do we know about those? Strong base. Okay, so strong bases are not acidic. NH3. This one has to come just from a little bit of experience. What's NH3? It's a weak base. It has a Kb. You probably saw it in your homework a few times. So NH3 is a weak base. It's also something you'd be able to look up in a table on the exam. You'd see NH3 has a Kb, which means it's a weak base. This one's a little bit harder. If this is the right answer, Fe3+. Why is the iron 3+ acidic? Yeah, highly charged metal ion, or highly charged ion. It has a charge on it greater than or equal to +3. And those are going to be acidic. What they actually do, so, those metal ions, remember, when they're in water, water surrounds them in that hydrolysis with metal ions. We talked about that last semester. And those highly charged ones start pulling in those electrons, and they weaken an OH bond on one of those water molecules, and one of those hydrogens floats away and makes it acidic. That's why you hear about acid mine drainage being such an issue, because those heavy metals can react with the water and actually turn the solution acidic. And then E, NABR. So this has a neutral cation and anion. Okay, because sodium is the counterion of a strong base. Br minus is the conjugate base of a strong acid. Neither of those things have any acid-base properties, so that would be a neutral salt. So, all right, good. We're about halfway through the time, about halfway through the problems. That's a good sign. Number 13. Yeah? Okay. So for 13, you just really have to be able to recognize your strong acids and your strong bases to see, what's what. So for 13, we have HCl and NaOH. Okay, so we're looking for a weak acid and a strong base. Is HCl a weak acid? Nope, it's a strong acid, so that one doesn't work. We have HF and NH3. Okay, HF is a what? It's a weak acid because it's not one of your 6 strong. NH3 is a what? Weak base. So this is weak acid, weak base. It wanted a strong base, so NH3 means that one's not going to be right. C is HCN and F minus. Okay, HCN, weak acid, that's good. F minus, conjugate base of a weak acid, which means it's a weak base. So the F minus ends that one. It's D, HClO, and barium hydroxide. Okay, HClO, weak acid. It's not one of the strong acids, so it must be weak. And barium hydroxide, group 2, metal hydroxide. That's going to be a strong base. So this is a weak acid with a strong base, which is what it's looking for. So that's why D is the answer. If we look at E, we'll just go ahead and look at it. We have HNO3 plus Cn minus. HNO3 is a what? Strong acid. They wanted a weak acid, so that's not right. They also wanted a strong base. Cn minus is a weak conjugate base from a weak acid, so that doubly doesn't work. So the only one that fits there is D, the HClO and the barium hydroxide. That's the only way to do it. You've got to go through it a little bit at a time to see what you can eliminate. There's no way most people will just look at it and go, oh yeah, it's that one. So you've got to take a little time on that one. Let's see. So number 14. Yep. I wasn't even going to ask because I figured somebody was going to say yes. All right, so we want to know if we mix equal molar amounts. In other words, they completely neutralize each other here. For these following pairs, which will leave a basic solution. Okay, let's see. So that first one, we have HCl and NaOH. So strong acid, strong base. What do we get when we mix a strong acid and a strong base? We get a neutral solution. Okay, neutral is not basic, so that's not right. B is HNO3 and Cn minus. Okay, well, we can take a look at the products there. That's going to give us NO3 plus HCN. HCn's an acid. That's going to hydrolyze in water and give us H3O plus Cn minus. Okay, so what's that going to be? That's going to be acidic because we have an equilibrium that gives us H3O plus. Okay. This is a case of looking, it's like, ooh, so this is a 100% reaction with a strong base, strong acid and a weak base. It leaves us a neutral anion and a weak acid. That weak acid is then going to react with water. and give us an acidic solution. Okay, the C part, H2SO4 and KOH. Okay, H2SO4 is a what? Strong acid. KOH, strong base. So that's going to be neutral. Should write acidic on this one here. Neutral's not right. D is H2O and KBr. Okay, so basically I'm just going to take KBr, potassium bromide, and dissolve it in water. What's that going to do for me for a solution? What's that going to give me? What's that? Yeah, so we got Br minus, conjugate base of a strong acid HBr. So that's ineffective as a base. K, counter ion of the strong base potassium hydroxide. So that's ineffective as an acid. And so we have a neutral salt. So we're putting a neutral salt in the water. It's going to have a neutral solution. Okay, and that leaves us with the last one. So that formula there is just acetic acid. I'm just going to write it as HAC plus NaOH. Okay, we know how that reacts there. We're going to get water. We're going to get a sodium ion. And we're going to get an acetate ion. You know what that acetate ion is? The conjugate weak base of acetic acid. So that's going to react with water. And in equilibrium, give us HAC plus OH minus. And because that makes OH minus, that is going to give me a basic solution. It's a hard problem to work out. Yeah.
So for the same problem in the second answer.
Here?
So yes.
Okay.
So the reason it doesn't, ice-box for NO3 minus is that because it's the conjugate of a strong acid.
Yes, exactly. And it has no acid properties. It has no base properties. Yeah. All right. Let's see. Number 15. Yeah? So we didn't talk a whole lot about common ions. But if we have this salt here, sodium nitrite, when that goes into water, it's a sodium salt, so it completely dissolves. Gives me sodium plus.
Can you move the paper up a little bit?
Is that better? Yeah, I know. My inner smartass does come out once in a while. If I'm at home, it comes out all the time. So for common ion, all we're looking for is an ion that's common to what we just put in there. So it's going to be either sodium or an NO2 minus. Sodium wasn't one of the choices, so NO2 minus. Because it's common to one of the salts. That's all it is. So it's not the best common ion problem, I'll grant you that. There's definitely a better one to ask, but that's the one that was in the test bank. All right, number 16. Is that a yeah? Yes? Okay. So 16, so in a reversible chemical reaction, so all that means is that it can reach equilibrium going forward and reverse. We have a situation at some point where Q is less than K. Okay, so remember that Q can be taken at any time. K is at equilibrium. But they're both equal to, essentially, concentration of products over concentration of reactants. Okay? So those are our equilibrium concentrations. And Q is equal to the same thing. It just doesn't have to be at equilibrium. Okay? If my number for Q is too small, what does that mean when I compare this value over to here? It means I don't have enough product and I've got too much reactant. That's what's going to make Q less than K. If the product value is smaller or the reactant value is too big. And that means that my reaction still has to move in the forward direction to make more product and use up some of the reactant to bring that number down. Okay, so that's why the answer there is B. Okay, so if Q is less than K, then products has to go up and reactants has to go down. Does that make sense to everybody? 17. Okay, so this one says, which of the following species has the largest Ka? So, which one of these can we pretty much throw out right away? Yeah, E, sodium hydroxide. We're looking for the Ka, so something that's a weak acid. Sodium hydroxide is a what? Yeah, it's a strong base. It doesn't, we don't really measure the Ka of a strong base. Certainly not as, reference to a large Ka. It probably has a Ka. It's exceptionally tiny. So we're left with these related species here. We have PO4 minus, HPO4 2 minus, H2PO4 minus, and H3PO4. So, and we talked about the dissociation. So remember H3PO4 plus water goes to H2PO4 minus. I'm not going to write out everything else. We have H2PO4 plus water goes to HPO4 2 minus, and HPO4 2 minus plus water went to PO4 3 minus. Now obviously there's H3Os on all the rest of that. And what do you remember about the size of the equilibrium constants for each one of those steps? It always gets what? Smaller. Okay, it's harder and harder to take away an H. So which one of those reactants is the strongest acid? The one with the largest Ka. I guess that's what it's asking for. The largest Ka, so that's going to be which one? It's going to be the first one, okay, because that's the easiest to lose in H+. And if it's easiest to lose the H+, it's going to have the largest Ka. Okay, so as we went down, the Ka's got smaller and smaller. It's harder and harder to take that H off the more you try to take off. Okay, so the answer there would be H3PO4. Okay. Questions on that one at all? Very much a thought problem on that one. A little bit on 18 as well. You guys want to see 18? Yeah, I figured because I got asked that a lot in class. Let's see. So we want to know which is the strongest acid. Now, there's two ways you can do that. So we learned two different ways of looking at this problem that will both get us to the correct answer. Okay, the first way I think is the easiest way. So HClO4 is a what? It's a strong acid. It's one of the 6 strong acids that you need to know. All of the others are what? They're weak. So the strong acid is definitely stronger than any of the weaks. So it's got to be weak. The other thing we learned, however, is that the number of oxygens on the central atom increases the acidity. So the HClO4 has the largest number of oxygens on that central chlorine, and that's going to make the H easier to come off. And so, again, HClO4 comes up as the strongest acid. The little goofy standout there is the HCN, but of course HCN is a what? It's a weak acid, and chances are it's not going to be the strongest one on there. Okay, so that's why 18 is A. All right. I'm sorry, go ahead.
Real quick, so it asks what's the strongest acid that had HClO4 and something like HCl or hydrochloric acid.
You don't really have a way. We just call them strong. In water, they're the same strength. Yeah. Now, they could ask you like HCl, HBr, and HI. And we learn that as you go down, they get stronger. But yeah, if it's not a trend like that, there would be no way to ask that. Yeah. All right. Number 19. Yeah. So 19 is kind of silly as a problem. When you see the answer, you kind of go, oh, yeah. So we have a solution of sodium acetate, and we're adding acetic acid to it. So we're adding an acid to a solution. What's the pH going to do? It's going to go down. That's it. We're adding acid, the pH goes down. That's what happens to every solution. If you add an acid to a solution, the pH is going to go down. So that's why the pH decreases. All those other answers make it sound like it's something much bigger, and it's not. All right, let's see. 20. Yeah, okay. Yeah, I think I can get 20 on this page. Might be a little bit of a stretch, but we'll try it. All right, so we want to know the pH of a mixture of 0.5 molar HNO2 and 0.5 molar NaNO2. Okay, so what we see is that we have HNO2 and NaNO2. Okay, NaNO2, of course, is going to break apart into Na plus and NO2 minus. So really what we have is we have a solution of HNO2 and NO2 minus. We have an acid and its conjugate weak base, which means that this is a what type of solution? It's a buffer solution. If it's a buffer solution, which equation do we get to use? Yep, the Henderson-Hasselhoff equation. I know it's Hasselbeck. It's so much easier to say Hasselhoff. All right, so since we can use that, we know that the pH is equal to pKa plus log, and if we write out our Ka, because we're given a Ka for the HNO2, we see we have HNO2, so we're just going to write the acid dissociation for HNO2. Anytime we write an acid dissociation, all we're doing is writing it with water. It's reacting with water, hydrolyzing, that's what that means, and the acid's going to lose an H plus to water. We're going to get H3O plus and whatever the conjugate base is. Okay? And the reason I wrote that here is so that we know what to put on our equation here, so we can do products over reactants from our buffer components in our equation here. So that's going to be concentration of NO2 minus our product over our reactant HNO2. Okay, and now when we work that one out, we find the pKa, so we take the negative log of the Ka and we get 3.35 plus log of the NO2 minus concentration, which is 0.5, over the HNO2 concentration, which is also 0.5. Well, that wasn't very helpful. So 0.5 over 0.5 is 1. Log of 1 is 0. So the pH is equal to the pKa, and that's 3.35. So the answer there would be C. Yeah. So by looking at the components we were given, so we have HNO2 and NaNO2. NaNO2 is going to break apart into sodium ions and nitrite ions because it's a sodium salt. And so really what I have in solution is HNO2 and NO2 minus. That's a conjugate pair, which means we have a buffer solution. So a buffer is made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. And we have both of those present in the solution. Barely fit that on that page. All right, that was 20. 21, yes. So we want to know what is the pH of 100 milliliters of a 1 molar HCl solution after 30 milliliters of 2 molar sodium hydroxide solution are added together. So this is actually stuff that we covered today in class. I don't think I've got any of this on the test, but I will go ahead and work it out just in case I made a mistake. So we want to see what we've got. We've got HCl. It's a strong acid that is going to react with the strong base. They're not conjugates of each other, so they're going to react. The acid and base are going to react. And so that's just going to give us water and NaCl, neither of which we really care all that much about. Okay, so we want to count, because we're having a reaction take place, we want to icebox that, and we need to work in terms of millimoles. And I know if you were in Dr. G's class, you probably haven't talked about, you may not have talked about millimoles yet. So to get millimoles, all you do is you take the milliliters times the molarity. And all they are is just thousandth of moles. Just like we have milliliters, these are just millimoles. But they're much easier to work with. So for the HCl, the number of millimoles, we have 100 milliliters times 1 molar. So that's 100 millimoles. And for the sodium hydroxide, we have 30 milliliters times 2 molar. And so that's 60 millimoles. I don't really care about the water or the NaCl. So because it's a strong acid and a strong base, anytime you've got something strong in there, they react to the death. They go until one of them's completely gone. And it's going to be whichever one's present in the least amount. And so that's the sodium hydroxide. So there's going to be minus 60 millimoles of sodium hydroxide, and that's going to be minus 60 millimoles of the HCl as well. And so there's not going to be any sodium hydroxide left. And we're going to have 40 millimoles of strong acid HCl left. Right? Now I can take that 40 millimoles of HCl and calculate a new concentration. So my new concentration of HCl is going to be equal to 40 millimoles. And to do concentration with millimoles, you just do millimoles over milliliters. It's just like moles over liters, except it's all millis. So everything cancels out very nicely. My new volume here is 130 milliliters because I had 100 milliliters of acid and I added 30 milliliters of base. That's going to give me 130 milliliters of solution after the reaction took place. And when I do that, I get a concentration of HCl of 0.307 molar. Now, because this is a strong acid, remember the concentration of a strong acid also represents your concentration of H3O plus in that solution. And so since I know my concentration of H3O plus, I could just find the pH. So that's going to be equal to the negative log of 0.307, and that gives me a value of what? 0.51. So that's a pretty strong acid solution right there. Questions all on that one? Okay. That was 21. Let's see. 22. So 22, that I definitely will not ask on the test. That's a titration question, so I'm not going to go over that one here. That's a titration question. We're not going to have titration stuff on the test. Let's see. 23. Yes. How are we doing on time? Doing okay? So we're looking for the acid dissociation constant. We're given the acid dissociation constant, Ka, which is missing here, but it doesn't matter because it gave it a name. For gallic acid is 4.57 times 10 to the minus 3. What is the base dissociation constant for the gallate ion? So, you don't really know the formulas here, which isn't terribly important. Kind of what you need to know is that those two are going to be conjugates of each other. Just like we have acetic acid and we have the acetate ion. You have gallic acid and the gallate ion. Okay, -1. And so what we know about the Ka and Kb's of a conjugate pair is that the Ka times the Kb is equal to kW for a conjugate pair. And so Kb is going to be equal to Kw over Ka. So that's equal to 1 times 10 to the minus 14 over 4.57 times 10 to the minus 3. And we get a value there of 2.19 times 10 to the minus 12. Okay, we should probably put the formula in for the gallic acid and the gallic ion just to help out. I wouldn't give you anything that you either can't find on the sheet or shouldn't already know. Now let's see, 24. Yeah. Okay, so 24, what we're doing here is finding the pH of a salt solution. Okay, the pH of a salt solution. Because we have Kf, we have metal and a non-metal, K and F, so we have an ionic compound. And it's a group 1A metal compound, so we know it's going to be completely soluble. So we know that Kf is going to react in water, or dissolve in water, to form K plus ions and F minus ions. Now the K plus potassium ion, counter ion of a strong base, KOH. F minus, however, is a what? Conjugate base of the weak acid HF, and that means that it is a base. And because it's a weak base, it will hydrolyze in water and react, okay, as a base. So that's kind of the hard part to do here. So the F minus is going to react with H2O in an equilibrium, and that's going to give me HF plus OH minus. We want to icebox that. So my F minus concentration is going to be 0.15. We got no HF and no OH minus present. We're going to lose some of that F minus. It's going to give us some of the HF. It's going to give us some hydroxide. So 0.15 minus X, X, and X. I know a lot of people struggle with writing that second equation there. Okay, just remember, anytime we're entering that equilibrium for an acid or a base, we're reacting it with water. And because this is a base, it's going to take an H from water. If we'd have had an acid, then it would just give an H to water. Okay, but it's always that reaction with water when we have those weak acids and weak bases. Now, the issue here is that this is a base dissociation, so I have to use a Kb here. So that Kb is going to be equal to X times X over 0.15 minus X. The problem is I don't have a Kb for F minus. The problem gave me the Ka for HF, not the Kb for F minus, and they are not the same thing. So you've got to make sure you don't use the Ka in a Kb reaction. You've got to find that Kb. And that's not hard, we just did it up here. So for a conjugate pair, we know that Ka times Kb is equal to Kw. So we know that Kb is equal to Kw, 1.0 times 10 to the minus 14 over the Ka, which is 7.0 times 10 to the minus 4. And so we get a Kb here that's equal to 1.43 times 10 to the minus 11. Okay, so this is equal to 1.43 times 10 to the minus 11. Very small value for K. We're going to have a very small value for X that we're subtracting from the 0.15. So we're going to ignore that X. And that means we end up with X squared over 0.15. We solve that for X, and we get an X value of 1.46 times 10 to the minus 6. And again, we look back at our ice box and we see, what does X equal? Well, X is equal to the concentration of OH minus here. So we need to calculate a POH by taking the negative log of that. And so we get a POH of 5.83. And we end up with a pH by subtracting that from 14. And we get 8.17. which we would expect that to be basic because we have a conjugate base in solution, F minus in solution. Questions at all on that one? I know those are some of the harder ones that you guys do. All right. Last couple. A little bit over time. That's all right. I hope that's all right. 121 is probably trying to get in here. 25. So we got to remember what we want to have for a buffer solution. We've got to have a weak acid and its conjugate weak base. So there's 3 of them on here we can throw out right away. Which 3 are they? B, C, and D. And the reason we can throw those out is because HI, HBr, and HCl are all what? They're all strong acids. Strong acids don't make buffers. So we can't have a buffer solution. So it's either A or it's none of them. Okay, so for A, we have CSF. Okay, cesium's group 1A metal. And F minus, so that's going to break apart into cesium plus and F minus in solution. And then we have HF, which of course is a weak acid, so we have a source of F minus and HF. So HF is a weak acid, F minus is its weak conjugate base, that makes a buffer. Okay, so A is the answer there. Okay. How about 26? 26 is missing a very important piece of information. You're missing the concentration of the potassium acetate. It is going to be 1 molar as well as the acetic acid. Okay, so we're looking for that pH. So we have acetic acid. We're given a Ka for acetic acid. So we want to write out the Ka expression or the Ka dissociation. We get H3O plus AC minus, and we're not adding anything to this one. So pH is going to be equal to pKa plus log concentration of acetate over concentration of HAC. And so when we take the pKa, we get 4.74. We have log. They're both going to be 1 molar. So those are going to cancel, and we end up with, again, the pH equaling the pKa of 4.74. I know it says 4.77. I don't know why it says 4.77. It should be 4.74. But that's how you get that one there. All right. Pretty much at an hour. I hope you found that helpful. Again, don't use this as the only study guide. This is just a sample of problems from a test bank. I will get this pencast posted as soon as I can, hopefully before 9 o'clock.